In this lecture, I will give an overview of statistical learning. Most of the material, meaning the figures, are from the ISLR book and the ESL book. These are books that are stated in the syllabus. Okay, so let's start. What is statistical learning? Well, statistical learning, roughly speaking, refers to a vast set of tools for understanding data. And these tools can be classified as supervised or unsupervised. Supervised means that there is the presence of an outcome variable that guides the learning process, such as regression and classification. So you have an outcome variable, and then you have a set of features, or also known as predictors, or also known as independent variables. So you have a set of predictors, independent variables, features, whatever you want to call it. And then you have this outcome variable, which is a response, also known as a response or dependent variable. And we like to study the relationship between the outcome variable, the response, the dependent variable, and the many independent variables. And this itself can fall into two categories. If the response variable is continuous numeric, then it's a regression problem. And the simplest kind of regression is logistic regression. And then if the response variable is categorical, if the response variable refers to classes, groups, then we call it a classification problem. Now here you may say, well, what about logistic regression? Logistic regression tries to categorize, classify into two groups, for example. Why is it called regression? Well, I mean, these definitions are not super clear-cut. But when we refer to regression, we mean that the outcome variable is numeric, continuous, and when we're talking about classification, the outcome variable is categorical. Unsupervised learning, there are inputs, but no supervising outputs. And we just like to learn the relationship and structure from such a data. And itself, unsupervised falls into two classes. One is clustering and the other one is dimensionality reduction. Clustering clearly refers to you have many data points. These data points, imagine that each data point refers to an item or an individual, and you like to summarize these many data points into groups in which the data points that are within each group are more similar to each other than data points that are not in the same group. Now then the question becomes, what does it mean for two data points to be similar? This is something we'll discuss. Dimensionality reduction, such as PCA, which is the simplest dimensionality reduction, is essentially you have data points with many features, but you know that the underlying structure is much lower dimensional than what the data looks like. And that's called dimensionality reduction. Here's a classical example of classification. So we have handwritten digits, and everybody writes differently. though all of us understand that these are all zeros, these are all ones, these are all twos, threes, etc. And we like to have a statistical learning technique or algorithm that if you give it this image as an input, it will say 0. If you give it this image, it will say 9. Okay. So this is clearly a classification problem. Now the question is, what are the features, or what are the predictors? The predictors are the pixels. So every single pixel in one of these is a feature, and that pixel is either very dark or white, so it's intensity, and typically this intensity is something between 0 and 1. So 1 is black, 0 is white, and the image is a 16 by 16 8-bit grayscale map. And well, it's not between 0 and 1, it's actually between 0 and 255. So each pixel, the intensity ranges from 0 to 255. And essentially, we want to predict from the 16 by 16 matrix of pixel intensities the identity of each image, which is either 0, 1, 2, 3. So how many features do we have here? 16 by 16, which is 160, and then there's 60, 96, so around 256. Okay, so 256 features. And why is it supervised? In a sense, the algorithm needs to see some examples, and these examples need to be labeled. So somebody has looked through many handwritten digits from US postal envelopes and marked them. This is a 0, this is a 0, this is a 1, this is 2, and this is created, this is put together into a data set. And then this data is given to the statistical learning algorithm, and then the algorithm learns the relationship, and the next time if you give it a new digit, it will be able to classify these digits. And this data set specifically is available on the website of the book Elements for Statistical Learning, the ESL book. If you just search it on the website of the book, if you look at the data, this is the web page of the book, and if you, here you can look for some of the errors that may exist in the book, but what I was referring to was the data which is here. So there are these training for zeros, ones, and to 9, and essentially all the data that is used in the book is available here. Okay. Now here's an example of unsupervised learning. This is a DNA expression microarrays example, and DNA microarray measure the expression of a gene in a cell by measuring the amount of mRNA present for that gene. So microarrays are considered a breakthrough technology in biology, and it allows us to do a quantitative study of thousands of genes at the same time from a single sample of cells. Okay, so what are we looking at here? Each row refers to one gene, and each column refers to a sample. So here we have around 7,000 genes, although we don't see them all, and we have 64 samples. Okay. And this is what we call typically a heat map. It's a very useful way of presenting data. And green means negative, red means positive, and the samples are 64 cancer tumors from different patients. So you see, there are many genes we have that we are measuring, but we do not have as many samples. And the big question here is how genes and samples are organized. The typical questions include the following. Which samples are most similar to each other in terms of their expression profile across genes? Because if you figure that out, then you can say, oh, maybe these patients have a similar expression of genes, so maybe their treatment should be similar. Maybe if we know something from this patient, we can apply to the other patient. Another question is, which genes are most similar to each other in terms of their expression profile across samples? And do certain genes show very high or very low expression for certain cancer samples? So these are all questions which can be addressed using unsupervised learning, because there is no specific outcome. Here's another example which is about spam versus non-spam. This is information of around 4,600 email messages in a study that tries to predict whether the email was junk or not. So the objective is to design an automatic spam detector. And for all these 4,600 emails, we have the true outcome. We know whether it's a spam or whether it's not a spam. And we also have the relative frequency of 57 of the most commonly occurring words and punctuation marks in the email message. So this is a supervised learning problem with the outcome class variable being email or spam. So it's a classification problem. And again, this data is available on the website I just showed you. Another thing that becomes really important when we focus on classification is there's a difference between different types of error, and this is a concept you have seen before. When it comes to hypothesis testing, there is a difference between type 1 error and type 2 error, and we will address it in the lectures. And there's a way to quantify or subjective or domain-specific belief about how costly each type of error is. For example, when it comes to the email example, we want to avoid filtering out good emails, while letting spam get through is not desirable, but it's better to have a few spam in your email than not to receive the important email you have been waiting for. Okay, so this is, now we're moving to chapter 2 of the ISLR book. And we're just looking at some data. It's about advertising data, and it's about seeing how sales are related to different budgets spent in different mediums for advertisement. Okay, and each data point refers to a different market. So we have TV, radio, newspaper. Obviously, all of them, the more money you spend, sales go up. The relationship is different, but it looks linear, right? And that's what we all know from many years ago. Linear regression looks the right thing to do. But what if something that looks linear is not really linear? I mean, how can we determine whether the relationship is really linear or it's actually nonlinear? Here is a nonlinear relationship, and this curve here essentially shows the underlying relationship. Obviously, there's always some fluctuation when you gather data, but the true relationship between income and years of education is not linear, at least in this example. And here you only have one variable, so it's easy to just plot it and look at it, but things get quickly more complicated when you have more predictors, more features, more independent variables. And here's an example. I mean, this is still 2 variables, so we still can't plot it, but you get the idea. If we have more than 2, then we cannot plot this. Okay, so income versus years of education and seniority. This surface here expresses the relationship that might exist and we like to capture, but obviously we only see data points. And this is an example where let's just assume that this surface is the true relationship, and you can always think of data that data is a noisy version of the reality. Okay, we do not care about data itself. We care about what we can get from the data. So in this context, for example, we do not care about these individual data points. What we care about is what is the underlying relationship here, this underlying surface that gave rise to this data. Okay, and one big question here is this, like, how do we know whether this relationship should be linear? Like, if you do linear regression, essentially what we are doing geometrically, linear regression is trying to find a hyperplane. Well, this is a plane in 2 dimensions, but if we go more than 2 dimensions, we call it a hyperplane. Essentially a hyperplane that is as close as possible to all the data points. So you only see these red dots. So how can you know whether just doing something like a linear regression is all right, or you need to find something more sophisticated that is more flexible, and for example, a rough thin plate spline fit to the data might be a better fit or might explain the data better. And this is a question we will learn how to answer. Okay, but essentially this is a framework that we will work with. I mean, this is what I write. What we're looking here is just applies to regression, and but later I will express the same thing for classification problems. Okay, so but for regression, more or less, I mean, one of the very common ways of modeling is that there is a response, there is this unknown function that represents the relationship, and then you have x, which is a vector of features, and it passes through this function. There's some noise added. This noise is some irreducible error. It's a random error, and essentially everything that cannot be explained in the response by x, we just is just expressed by epsilon. So there is nothing. Epsilon is just some random noise, and it basically captures anything that x cannot tell us about y. For example, when it comes to income, obviously years on education and seniority play a big role, but there are so many other factors that go into income that they cannot be captured only by years on education and seniority, or maybe three other ones, and that's what epsilon represents. And the whole idea is that we like to learn f. We like to estimate it from the data. Okay. So why do we like to estimate f? Well, first of all, if we know f, which we use this sign hat to express something that we are estimating. So f hat means an estimate of f. We can use it for prediction. If tomorrow somebody comes with this seniority and years of education, whatever years of education, then we can plug it into this function, get a prediction. And the accuracy depends on two things. One is the reducible error, and the other one is the irreducible error. Obviously, f hat is not going to be a perfect estimate of f due to limited amount of data and maybe inaccurate statistical model. We use a linear regression when the relationship is non-linear. Here, imagine this is the true underlying relationship, and then the data doesn't fall exactly on this surface. If the data was falling exactly on this surface, then epsilon here would be 0. But epsilon is never 0. And for example, the reason that this is a little bit above this is maybe this individual had some other qualities that put her or him above the typical individual with this many years of education and this seniority, and that's why they get a bigger income. And you could argue the opposite of this, and that's all what we call the irreducible error. If we just know years of education and seniority, then there's just so much we can do. Now, on top of that, if we take this data and just fit a linear regression to it, then we are fitting a hyperplane. And then if we are fitting a hyperplane, then we are making a structural error here, obviously, because you see, here it's a little bit below, here it's a little bit above, but the linear regression model is unable to capture that, and that's what leads to what we call the reducible error, which is caused by two things. One is limited amount of data and inaccurate statistical model. Okay. Then now the this is a reducible error. Why do we call it reducible? Because if we had more data and if we use a more accurate statistical model, then we could make this smaller. But there is something, the irreducible error, that even if we had a perfect, like even if I told you what f is, even if an oracle would tell you what f is, then still you had this epsilon. And that's not something we can get rid of as long as we're just using these features. Okay. So how do we measure the accuracy of our prediction? Well, if it's a regression problem, it's just the average squared difference is a classical way of measuring it. It's not the only way. You can look at the average absolute difference and so many other ways. Well, let's just focus on this because this allows a nice split. In other words, you can show that the average square difference boils down to the square difference between the true unknown function and the estimated one squared plus the variance of epsilon. So this is the reducible error, this is the irreducible error. And the take-home message is that we should not expect more precision than the subject matter admits. In other words, the variance of epsilon is always going to be there, regardless of how well we perform here, how small this is, how small we can make this, regardless of how small we make this, this is going to be here. And we can make this smaller, the reducible error, by using a more flexible model. A thin plate spline is essentially a surface which is smooth. So it is like linear regression is a hyperplane, but imagine you allow that hyperplane to deform at some locations, so to be a little bit more flexible, so that fits the data better. And that's what it is, and we will later see that we can play with this, the level of flexibility of a thin plate spline. Okay, so why do we want to estimate it? Again, as opposed to prediction, we might just be interested in inference, which is to learn the association between the response and the predictors. In other words, which predictors are associated with the response. And typically in biostatistics, in the pharmaceutical industry, people are not that much interested in the prediction. They're more interested in learning an inference. Which predictors are associated with the response? The response can be the onset of a disease, or it can be the reduction of certain chemicals in blood, etc., etc. Okay, so the relationship is the focus. So it depends on what you're doing. In advertising, obviously, nobody is interested in, I mean, except for researchers, but in the industry, people are more interested in predicting whether somebody will click on this link or not. And in doing that, inference is a secondary objective. It's more prediction, and we will see that these two different objectives will lead to slightly diverging paths, though there's a lot of overlap. Okay, so here this is a good graph because it represents a trade-off between flexibility and interpretability. Essentially, when you care about inference, we typically work with what we call simple models, and they are typically just simple regression, simple linear regression, logistic regression, where we get the coefficients, and the coefficients are either positive or negative, and based on that we can say, okay, this feature has a positive impact on the outcome, this feature has a negative impact on the outcome, right? But if the relationship is more complicated, then we need to use more flexible models, and the more flexible they become, the less interpretable they become. So here we have subset selection, lasso, least squares, we have trees, and then we have support vector machines. So, and then you also have neural networks here, okay? Which means that these tools work more like really powerful black boxes, which can learn from the data, but they don't really tell us much about who is related to who, though there are some ways people are working on it. But at the very broad level view, obviously, regression, linear regression, you get the coefficients, you get the betas, and you can easily make interpretations based on that. But this is a nice trade-off. Flexibility reduces interpretability. Now here's an example of um, of what it means to do unsupervised. Because as we said, most statistical learning problems fall into one of two categories, supervised or unsupervised. And the examples that we have discussed so far, except for the gene expression, fall into the supervised learning domain. So unsupervised is somewhat more challenging because for each observation, we observe a vector of measurements, but no associated response. So it's not possible to fit a linear regression model or a logistic because there is no response variable to predict. And here's an example. You see each of these data points, they are colored separately. Okay, let's imagine they had the same color, the same sign. So each of these would be one data point. It has two features, and we like to cluster them. And the ideal cluster, just by visually looking at it, okay, these group of data points are closer to each other. These are closer to each other, so therefore they should have a separate, different colors and labels. Okay, so the idea is that you give these unlabeled, uncolored data points, and then after you perform unsupervised learning, this is what you receive. Okay. Now, just to show you how challenging this task to begin with is that first of all, most problems have more than two features, so you can't just plot them and look at them and say, oh, okay, this is what it looks like. And second, typically, in real life, there's no clear-cut clusters. Things are more complicated. They have overlaps. And when things have overlaps, it becomes really fuzzy because this one, for example, does it belong to this group or this group? So there are a lot of points that are in the border, and there are a lot of methods that actually allow clustering, where these are called soft clusters, where each data point is assigned a probability, 90% to this group, 10% to that group, 20% to that group. But at the very basic level, we have hard clustering, which just assigns each data point to one class. Okay, so what we do in this class is typically we represent training data that we have received in this form. So you have the x1, y1, this is one data point, and this is response for the first data point, and x1 is a vector. Vector xi is a vector, and this vector has p features. Feature 1, 2, 3, 4, p. And we have n data points. Okay? And this is essentially when it comes to supervised learning. Unsupervised learning does not have these y's. When it comes to supervised learning, this is how we present the data. And we can present it equivalent in a vector matrix format, where X is a matrix, n rows, p columns. N rows, that means that each row is one observation. P columns, that means n rows, each row is an observation. P columns, each column is a predictor, is an independent variable, is a feature. And then we place all the observations in one vector, y1 to yn. And an example of supervised learning is that we give you y and x, find f hat, such that f hat is close to yi. And when it comes to linear regression, just as an example, linear regression essentially is just saying that, okay, the response is x, the matrix, times the vector beta plus this vector epsilon, which is this noise. And how do we measure the closeness? With the residual sum of squares, where yi minus xi transpose beta hat. squared, which can be written in this form, where y minus x beta, this is called the L2 norm. So what is n, what is p is always the question we should ask, because throughout this semester we will use n and p to refer to the sample size and the feature size. Now, how can you measure model accuracy? And that's where there is a difference between training accuracy and test accuracy. Training mean squared error is essentially you look at the residual sum of squares, the mean of these errors, and basically it shows how well the model fits the data. But that does not necessarily mean that if you tomorrow had a new data point, previously unseen test observation that was not used to train the statistical method. So x0 and y0 are unseen data points, and the test MSE is actually the average. I mean, there needs to be a square here. I'm missing a square here, but you get the idea. But, and what is it averaged over? It's averaged over the unseen test observations. And these two quantities are not the same. As we will see, there is a phenomena called overfitting, which you may have heard in the past. And because of overfitting, train error tends to be smaller than test error. Okay. So train error tends to become smaller as the degrees of freedom becomes larger. So what is the degrees of freedom? Degrees of freedom is a quantity that summarizes the flexibility. It's a measure of model complexity. Roughly speaking, you can think of it as the number of parameters in the model. So if you're doing, for example, linear regression, it's the number of predictors. And we know that if you have a data set and you're doing linear regression, if you just add some garbage predictors, your residual sum of squares will just become smaller and smaller. And that's called overfitting. And you're increasing the degrees of freedom. So this is something universal. Whenever the model becomes more complex, more flexible, obviously it will fit the data better. But if it fits the data better, that does not necessarily mean that that model will be able to predict tomorrow better, because maybe it's just fitting to the idiosyncrasies of that particular data set, as opposed to capturing the relationship that represents the association between the response y and the independent variables, features, predictors. And what does overfitting essentially mean? That the less flexible model would have yielded a smaller test MSE. Okay, so take-home message is that train MSE becomes smaller as the degrees of freedom increase. Test MSE has a more complicated relationship with degrees of freedom. We will learn that later. And we will cover all these topics in depth as we go through the semester. Okay. Here's an example where the true underlying relationship is this black curve, but we do not observe it. We observe these circles, and these circles are noisy version of this. Some of them are above the black curve, some of them are below it, and we can go two extremes. One extreme is just to fit a linear model. Another extreme is just to fit a very flexible polynomial. I mean, here, what is it? It's a smoothing spline. So imagine it's a very flexible curve fitting procedure that tries to go as close as possible to all the data points. Obviously, the residual sum of square, or the MSE of the green curve, is smaller than the linear regression. But is that really what we want to do? Is that really the true objective, or are we being fooled? Well, Turns out yes, because as we know in this case, and in real life we don't know, so there are ways to know it, but that comes later, this underlying relationship is not as complicated as the screen curve. So the screen curve is doing overfitting. And on the other hand, the linear regression is too simple. It's not able to capture the true relationship, and it leads to bias. Why bias? Because it tends to underestimate y in this region and overestimate it here. So this curve here represents the training error, and this is the test error. As we can see, as the flexibility, which here refers to the flexibility of the curve of this curve fitting procedure here, smoothing spline, increases, the mean squared error becomes smaller because this curve becomes more flexible and is able to pass through the data points better. On the other hand, this is the test error, which means that if a random data point in this range was picked, let's say here, and then some noise would be added, what would be the performance? And we can see that this is the performance of linear regression, this is the performance of this very flexible curve, and this is the performance of the blue curve, which you see here is something in between these two extremes. And it achieves the smallest minimum, the mean square error that can be achieved. And our objective is to find what is the right level of flexibility. Flexibility 2 means there are two parameters in this model, and that's why it's linear regression. Simple linear regression has an intercept and a slope. Therefore, the flexibility is 2. And as the flexibility increases, the training error becomes smaller, the test error becomes smaller, but then if you have too much flexibility, then the test error will increase again. Okay. So this is partially part of the what is known as the bias variance trade-off, and essentially what it's saying, the bias variance trade-off, is that the test error, which is the expected value of y0 minus the mul squared, which is what we had here, this square that was missing, can be broken down into three pieces. One is the variance of the estimate, the other one is the bias of the estimate squared, and the other one is the variance of epsilon. So this is the irreducible error. Okay. Now, what do each of these terms mean? This is something that it takes some time reading different books, how they address it, and I try to do my best, but it's something that you should spend some time and come back and revisit it to get a better sense, and maybe even do some simulations. But what this is, let's look at the first step. Expected test error. So imagine you had a large set of number of training sets, and you would estimate f hat for each of them. So you would get different f hats. Now the question is, what is the average squared error? This is the expected test error. And ideally, you would like a small bias and a small variance. What is the variance? The variance is essentially the amount by which f hat would change if we estimated using a different training set. Here, look at this. This green curve is going up and then down, and then it's going up and then down. Why is that happening? Because there's this circle here, and then there's this circle here, and there's this circle here, and obviously this fitting method is trying to pass through these circles as close as possible. And that's why we have this going up and down, up and down. Now, if we had another data set from the same source, it might have happened that this circle would be a little bit below the curve, or a little bit above or upper and lower, right? And that would change the fitted green curve as well. So the green curve is heavily sensitive to perturbations in the data, and that's why it has a high variance. On the other hand, this linear regression, I doubt would change much, even if you would bring these circles a little bit down and this one a little bit up. It wouldn't change significantly. Therefore, linear regression, it's a simple model, has a very low variance, but it has a high bias. What is a bias? It's an error that is introduced by approximating an extremely complicated real-life problem by a much simpler model. So this is complicated, and then we use a simple linear regression. We introduce bias. So to summarize, flexible models lead to small bias, high variance, low variance, high bias, fitting a horizontal line to the data, even linear regression. Let's see. Okay. Now, classification, when it comes to classification, then we measure model, how do we measure model accuracy? Because the response is not a numerical response, it's a categorical, and we cannot use mean squared error, for example. And the other concepts that are used here are error rate, indicator variable, training error, test error, but essentially it is all about the probability of making a mistake, the probability that an email is misclassified, okay? And here what will happen is essentially that you have these features and then you have this response, and we like to learn this conditional probability. And if we had access to this, so instead of having that function, the function that was the f that we introduced here for classification problems, boils down to this conditional probability. If this is a new email, x0 is a new email, what is the probability that it is 1 or 0? 1 meaning non-spam, 0 meaning spam. And the concept of irreducible error here boils down to the Bayes classifier, a classifier that has access to this conditional probability. We like to learn it. But even if you had this conditional probability, there's an unattainable gold standard. There's this irreducible error. There's still some error. And that's where the Bayes decision boundary comes and the overall Bayes error rate. So these are a little bit more complicated concepts that I will get to in the next lecture by going into the math of it. But now I just want to introduce it so you're ready for the following week. Simple method is the k-nearest neighbors method, which is essentially just looking at the neighbors of a data point and seeing what the neighbors are saying, the k-nearest ones, and essentially taking the majority vote of anybody who's the k-nearest people around you. And nearest is a concept that we define it basically. What do we mean near? How are two data points considered near each other? Again, this is also something I will get into more detail. finally, here's a different approach to classification. So imagine that each of these circles is a data point. If they're orange, they mean 1. If it's blue, it's 0. And then you have two features. This is x2, this is x1, and we're trying to, from this, we're trying to learn how to classify future data points. Now, this is not something that's very popular and used, but it's an interesting idea. And what is essentially happening here is that, okay, you have these circles, and for each of these orange circles, you can have a response of 1, and then for the blue ones, you can have a response of 0, and then treat it as a linear regression, and just fit something, fit a hyperplane, and what you will get is that this hyperplane at exactly this place will have a value of 0.5, and if you pass it, it will be greater than 0.5, and if it's below it, it will be less than 0.5. So this essentially is dividing the feature space into two parts, and we can use this. So if you get a future data point here, you can say it's okay orange. If it's here, it's blue. This is from the ESL book, this image specifically. Now, on the other hand, the decision boundary can be more complicated. Like here, it's a linear decision boundary, and here we see an example where the decision boundary is cannot be captured by a simple line, and this data was created according to some probabilities and a model, and based on that model, because it's a simulation, it's a toy example, we know what this probability, conditional probability is, and therefore we can compute the base decision boundary, which essentially is saying that, okay, if you're on this side of the boundary, the probability is less than 0.5. If you're on the other side, it's greater than 0.5. Now, here's a illustration of how k-nearest neighbors work. Imagine we're talking about 3 nearest neighbors, and each of these circles is one of the observations, and we are interested in labeling this x. This x is an unobserved data point, but we like to know what if tomorrow we would see a data point here, what would be the label of it? Well, if you look at the 3 nearest neighbors, you have 2 blues and 1 orange, therefore the label of this would be blue. And this is how k nearest neighbors work. Now the question is, what should be k? Should we use 3 nearest neighbors, 4 nearest neighbors, 5 nearest neighbors? And here is an example where you can see how different, what will happen if you use 10 nearest neighbors for this example. So this dashed line is the optimal base classifier, essentially a classifier that is only suffering from irreducible error. Now, if you apply 10 nearest neighbors, you get this decision boundary, which is different from it, obviously, because this is the k. You know, the optimal base classifier is a classifier where if an oracle would tell us everything about the nature of data production, data generation, which is we never have access to it. But k nearest neighbors, we just take the 10 nearest neighbors for each data point, look at the majority, and then use it to label, and we see that it's doing more or less a good job in capturing this decision boundary. Now, what happens if you increase the number of neighbors or decrease it. If you decrease the number of neighbors, the extreme case of one nearest neighbors is essentially each data point looks at itself, which is terrible, because then what's the point of having all these data points? And you see it's a perfect fit. You have this island here which is separating this one blue from all these oranges. This is overfitting. The other extreme is when the number of neighbors is too big. Then you have this curve which is looking more and more like linear separation. Okay? So which of these two is more flexible? This one is more flexible. This one is less flexible. So when it comes to k nearest neighbors, as the number of neighbors you increase in k nearest neighbors, you are reducing the flexibility. It might be counterintuitive at first, but if you think about it, it actually makes sense. And here is what we see, what we expressed before, that the test error goes down and then goes up. So I say, wait a second, what goes down, what goes up, what are we looking at? Great question. Okay, here's what we're looking at. On the vertical axis, we have the error rate. Error rate is the probability of misclassifying a point. It's a binary classification problem, and this dashed line represents the optimal base classifier. This one, which if an oracle would have told us what this conditional probability is, then this is as good as we could have gotten. Now the training error is just we have the data and we are, now what is this? Is 1 over k. Why is it 1 over k? Sorry. Typically, when we plot the error rate versus the flexibility, here is small flexibility and then we increase the flexibility, okay? And as we said, as we increase the number of neighbors, we are reducing the flexibility. That's why it's plotted using 1 over k. And as we increase the flexibility, the training error becomes smaller, and you see it goes up and down, up and down. You may say, well, this point is more flexible than this, why it's going up. Again, when we say this, there are always fluctuations, but the general trend is that the training error reduces as we increase flexibility. The test error goes down and it goes up. And this is the right level of flexibility we are looking, because it gives us the smallest error rate for new unseen data points. And it's actually as close as possible to the optimal lowest base error rate. Okay. So this is essentially the first 2 chapters of the Introduction to Statistical Learning. Thank you for your attention.